A URL shortener looks ridiculously simple at first. You paste in a huge link, get back a tiny one, and that feels like the whole product. But the second that tiny link starts getting hammered by traffic, this stops being a simple tool and turns into a real system design problem. So let's break it down and see what actually has to happen behind one little redirect. On the surface, this product does one very simple thing. It takes a long, messy URL and turns it into something short, clean, and easy to share. And that is exactly why it feels so simple to users. But under that simple idea, there is a lot more going on. So now the question becomes, what does the system actually need to do? A real URL shortener is not doing just one job. It has to create links, redirect users when they click them, and let someone manage or disable those links later. That already gives us a rough API shape, one path for creating, one for redirecting, and one for management. And once that part is clear, we can ask the question that really shapes the architecture. How much traffic are we building for? This is where the design starts getting real. Even if link creation looks small per second, that number adds up to a lot of stored data over time. And once you stop thinking only about averages and start thinking about peak traffic, the design choices matter a lot more. But writes are only the beginning because the bigger problem starts after people click. Creating the short link is the easy part. The expensive part is what happens after that link gets shared everywhere. Redirect traffic can be way bigger than creation traffic, which means reads are going to dominate latency, cost, and scaling pressure. And that tells us exactly what part of the system we need to optimize first. This is a very read-heavy system. You write once when the link is created, but you keep reading every time someone clicks it. So instead of thinking about this like a balanced app, it makes more sense to think of it like a redirect engine. And once that becomes clear, we can draw the simplest possible architecture and see where it breaks. The first version is exactly what you would expect: one backend service and one database. It is simple, easy to build, and for low traffic, honestly, a perfectly fine place to start. But simple architectures can hide future bottlenecks, so now let's zoom in and look at the data. The good news is the data model is pretty compact. We mostly need the short code, the original URL, and a bit of metadata for things like expiration or disabling a link. That means the lookup key matters a lot because every redirect depends on finding that short code fast. And once the schema is clear, the next question is, how do we generate these short codes? There are two common ways to generate the short code. One is random generation, which is simple, but now you have to deal with collisions. The other is taking an ID and converting it to base 62, which feels more deterministic but comes with its own trade-offs too. Either way, the database still needs to guarantee uniqueness, because this tiny code is at the center of the whole system. Now let's follow what happens when someone actually clicks one of these links. The browser hits the short URL, the backend looks up the original destination, and then returns a redirect response. That sounds fast and simple, but there is one important detail here. Every click depends on a database read. And that is exactly where the naive version of this design starts running into trouble. The problem is very straightforward. Every redirect goes directly to the database. So if one link gets really popular, it can hit the database over and over again, even though the answer never changes. That makes the system slower, more expensive, and more fragile right when the product is succeeding. And that points us to the first big optimization. This is where Redis starts to make a lot of sense. If the same popular links are being requested again and again, we can put a cache in front of the database and serve those repeated lookups straight from memory. Now the database stops being the default path and becomes the fallback path. And that can make a huge difference for redirect performance. In the best case, the request hits Redis and never touches the database at all. That means much lower latency and a lot less repeated pressure on the main database. For a system like this, that is the ideal path. That is where we want most clicks to go. But of course, a cache will not hit every single time, so we still need a plan for misses. When Redis misses, The system falls back to the database, fetches the original URL, and then writes that result back into cache. So the first request takes the slower path, but the next ones get the faster one. That gives us a really nice balance between durability and speed. But the second we add a cache, we also create a new problem, keeping that cache correct. A cache is only useful if you can trust it. If someone edits a destination URL or disables a malicious link, and the cache still has the old value, users can get sent to the wrong place. So cache invalidation is not some side detail here. It is part of the core design. And once you see that, a bigger idea starts to show up. Maybe not every request should go through the same service. At this point, the system is trying to do two very different jobs. Management operations care about correctness, updates, and business rules, while redirects care about speed and huge read volume. So, splitting those responsibilities into separate services makes the whole system cleaner and easier to scale. And once we do that, the storage layer can evolve in a smarter way too. Now, the database layer can specialize as well. Writes still go to the primary database, but cache misses on the redirect side can read from replicas. That takes pressure off the primary without making the write path more complicated. And if we want even lower latency, we can push caching even closer to the user. For very hot links, even reaching the redirect service can become unnecessary work. A CDN can cache those redirect responses at the edge, closer to users around the world, which cuts latency and reduces origin traffic even more. That means the hottest requests might not even touch our core system at all. But performance is only part of the story because URL shorteners also have a trust problem. If we are not careful, a URL shortener can turn into a phishing or spam machine really quickly. That is why things like rate limiting, blacklists, link scanning, and preview pages matter just as much as caching and replication. Good system design is not only about handling traffic, it is also about protecting users. And once those guardrails are in place, we can finally look at the complete architecture. Now we can see how all of this comes together. Reads go through the CDN, then the load balancer, then the redirect service, cache, and replicas, while writes and management operations follow a separate path into primary storage. Every component has a clear job, and every optimization is solving a specific problem. And that is what turns a very simple idea into something fast, scalable, and much more robust. The big takeaway is that this system only looks simple from the outside. Under the hood, the key idea is separating two very different priorities: correctness when links are created or updated, and speed when links are resolved. Once you separate those two paths, the rest of the architecture starts making a lot more sense. And that is the real trick behind designing a scalable URL shortener.